Well, today we're going to look at what's called Simpson's rule for approximating definite integrals, and we'll develop where it comes from and then see how to use it. It's very similar to the trapezoid rule that you watched the previous video on with the Think Well material. But with Simpson's rule, instead of basing this on a trapezoid, we base it on the area formula for a parabola. Now, we probably didn't even know that one existed, but the area for a parabola the formula for it is 1/3 and then x sub 3 minus x sub 1 all over 2, and then y sub 1 plus 4 y sub 2 plus y sub 3. Now, this is splitting our interval. We say the area under a parabola over the interval from x sub 1 to x sub 3. So our endpoints, well, we could call it A to B, but our endpoints will be x sub 1 and x sub 3. And then notice here we have y sub 2. That's our function value for what x sub 2 is. And x sub 2 is defined as, well, halfway between x sub 1 and x sub 3. So for this to work, we have to have three values, the two endpoints and then the midpoint, and then we can calculate the function values for that. So let's take a look at the parabola x squared plus 2x, and we'll go from 1 to 4. So x sub 1 is going to be 1. We'll calculate x sub 2 here, and then x sub 3 will be 4. What's halfway between 1 and 4? Oh, we add x sub 1 and x sub 3 and then divide by 2. So 5 halves, 2 and a half will be halfway between. So the area will be 1/3 times, well, x sub 3 minus x sub 1 over 2. And then the y values, that's your function values for these x's. Y sub 1 would be f of 1 plus 4 times f of 5 halves, and then plus f of 4. So we plug those values into our function, x squared plus 2x. Well, f of 1 will simply be 3. F of 5 halves, well, I'll let you plug that one into your calculator. And then f of 4, 16 plus 8 would be 24. So whatever f of 5 halves come out to be, and then multiply that by 4, add all that together, and then multiply this factor by, well, I guess 3 halves, and then times 1/3. And our area comes out to be, well, I already did this one, so I know what it should be, 36. So hopefully you can come up with the same value as you plug all this in. Now again, this is using the area under a parabola. Now in our work with the definite integral, we have faced problems of find the area under a certain function and above the x-axis. So we could set this up using an integral and make sure that we have the correct value here. Of course, the area formula should be easier to work with than the integral, but actually calculating the integral is easier. That's probably why we've never seen this formula before, because it does get a little cumbersome. But let's go ahead and integrate from 1 to 4 for this function x squared plus 2x. And we'll verify that that formula is in fact the area under a parabola. Well, to integrate this, antiderivative of x squared, antiderivative of 2x. Now you could say 2 times x squared over 2, but ultimately simplifies to x squared. From 1 to 4, and we get, oops, not 1/3, 4 cubed over 3 plus 4 squared, and minus 1/3 plus 1 minus that entire quantity. So what we get, 64 over 3 plus 16 minus 1/3 minus 1. Well, what we may want to do, 64 over 3 minus 1 over 3 would be 63 over 3, which turns out to be what? 21? 63 divided by 3. And then plus, well, 16 minus 1 is 15. And there's our 36. So the formula that we have does work. Which one was easier? Well, probably the integration, but before integration came about, before the fundamental theorem was discovered, mathematicians had figured out this area formula for the parabola. So, how does that work then as we think about maybe some integral, some area that we can't find the definite integral to, or can't find the exact value? We approximate, and like I said in the previous video, he showed the trapezoid rule. Well, we're going to look at Simpson's rule, which 1/3, and then you have your, instead of x3 minus x1 over 2, we're going to translate that into b minus a over n. And then with the last part of the area under the parabola, we had y sub 1 plus 4 y sub 2 plus y sub 3. Now we're going to split this interval up into many parts, not just 3 parts like this area of the under the parabola formula, but we're going to do this for the first subinterval. Okay. And then as we add a second subinterval and we look at the area under that parabola, okay, we'll call this first subinterval. Second subinterval, that's going to involve, well, instead of y sub 1, the first part of that second subinterval is going to be y sub 3. Then we'd have 4, y sub 4, and then y sub 5. Okay. And then the third subinterval, well, y sub 5 would be the first part of the third subinterval. And now these aren't multiplied by no means, but we're kind of showing where this formula comes from. As we think about adding the area under each one of these parabolas, okay, just like the trapezoid with adding all those trapezoids together, notice what's happening. We've got our first subinterval, then the second subinterval. Y sub 3 shows up again in the second subinterval. Okay. Then the third subinterval, well, y sub 5 is the last part of the second subinterval, and then the first part of the third subinterval. So the endpoints of each one of the subintervals is going to be used twice. Okay. So with that in mind, and thinking in terms of our partition the way we do it, y sub 1, well, normally we say a is x sub 0 rather than x sub 1. So the y sub 1 in our parabola formula will relate to f of x sub 0. Then we'll have 4 of the function value evaluated at our next x value. And then we'll have 2 of the next one. Then 4 of the next, and so on and so forth. And then finally, the very last one, very last parabola, x sub n, or b, is only going to show up once. It only gets counted once. So like the trapezoid rule, the first one and the last one only gets counted once, and then the ones in the middle get the either 2 or 4, depending on where they're at. So to kind of formalize this, to approximate a definite integral, the formula for Simpson's rule, 1/3 times the quantity b minus a over n times, again, the quantity f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2, and then we alternate 4, 2, 4, 2, and then finally the very, well, not the very last one, but the second to the last one will be 4 of that function value, and the very last one is just 1 of that function value. So that's Simpson's rule. The trapezoid rule looks somewhat similar, but in terms of area of all these trapezoids, 1/2 times b minus a over n, and then times the pattern there is just 1 for the first one and then 2 for the middle ones. And then finally, the very last one, we just have the 1. So a couple things to keep in mind. Simpson's rule, we have 1/3 and then times the b minus a over n. Trapezoid rule is 1/2 times the b minus a over n. And then your pattern, your coefficients of your function values, 1, 4, 2, 4, 2, 4, 2, 4, 1 for Simpson's rule, and 1, 2, 2, 2, 2, 2, 1 for trapezoid rule. Okay. Now, to show you kind of how this works, we're not going to go through all the steps on this, but I've done some calculations to kind of compare how this looks for how exact or how good an approximation it is, comparing it with some of the other things that we've done as well. So we're going to take a definite integral that we can calculate. Of course, you need to change this to x to the -2 and go through the antiderivative. We would end up with 1/3 as the exact value. But if we looked at this, first of all, if we did rectangles like we did last week, left endpoints on the rectangles, and, well, we'll use 4. 4 is kind of good, but not too many. It takes forever. But left endpoints, we'd end up with 0.3698811 and so on. Right endpoints, we would have 0.3004369 and so on. The trapezoid rule on this one would be quite a bit more accurate than the rectangles using left and right endpoints. 0.33511589 and so on. And then finally, Simpson's rule, 0.3333603 and so on. So by knowing the exact value here, we can see Simpson's rule is going to give you much more accuracy, especially than the rectangles, the right and left endpoints that we did last week. Trapezoid rule is pretty decent, although it's not even accurate to 3 decimal places. Simpson's rule is accurate to, well, 3, almost 4. You'd round up 0.3334, but that would give you pretty good accuracy. And if you want more accuracy, you just have to use more intervals rather than just 4. That's still pretty good for just 4 intervals. So that's Simpson's rule. Today we'll have a handout involving both the trapezoid and the Simpson's rule, and you'll be able to see how they're used in different ways.